homework shouldn't be due until Tuesday.
Yeah.
Because you're not going to watch the video.
Exactly.
It's all for dating. All right, it's all about dating. Here we go.
I'll be done.
So what do we know about lines?
They're straight. No, they're not.
Oh, dear.
They're not even straight.
How about something mathematical? How about y equals mx plus b? But then we learned there was a better way of writing a line. Do you remember what calculus kids were?
Y1
y minus y1 equals?
equals x1 m times x minus x1.
Woo! All right. So then we have this thing called constant slope, right?
No.
We're filling in characteristics.
Oh,
See?
we're writing it.
Oh,
here. That's kind of easy. What if we did it?
Characteristics.
Just didn't do math with that.
Y equals mx plus b.
Constant slope is called m, and m is found by, what's the formula for slope?
Y2 minus y1
Woo!
over 2 minus x1.
I'll take it. y2 minus y1 all over n2 minus n.
Oh, why is
One,
it?
which is the same thing as delta y over delta x, like the delta table we saw.
Why is it m2?
What's a delta?
Why is it
Oh, so I was having too much fun.
Yeah. Calm
Right.
down.
We're not
No application whatsoever. Alright, so x2 minus x1. You guys ever notice that when you're talking and trying to do something at the same time, it doesn't always turn out well?
Yes.
So when I make mistakes on the board, usually I'm talking and teaching and thinking about what you're understanding and thinking about what's coming next, and then sometimes the writing doesn't work out so well. So keep calling me on it if you're like, what? Because it might just be a mistake, like it was. But also a good life lesson that maybe those of you that do 1,000,010 things while you're doing homework, it's not the smartest approach. All right,
I'll
so
do homework wrong.
One on the bench.
anything else about a line? Oh, special lines. That's good. Special lines. We have vertical versus horizontal. We have vertical versus horizontal. Maybe I should have switched the order because horizontal lines are kind of like constant functions, so that's okay. Horizontal lines could be y equals 0x plus b, right? M equals 0. So that would be the same thing as a constant function. Whereas vertical lines aren't y equals a constant. Vertical lines are x equals a constant. And the way I like to remember it, think about the x-axis. An x equals is a tick mark on the x-axis extended. So go find the tick mark and then just make it long. That's easy. Whereas a horizontal, go find a tick mark on the y-axis. Go find whatever height you're supposed to be at, and then just extend it. Look, it's a horizontal one. Y equals. We have our identity function or a constant function that you guys already wrote down. Anything else? Linear functions will almost always have, oh, here's a good one. If m is greater than 0, don't I have an uphill slope? And if m is less than 0, don't I have a downhill slope?
Yes.
Because we're always looking at graphs or reading graphs left to right, like with the whole increasing, decreasing thing. I love these 4-colored pens. Snap. Are we ready to move on?
Hold on, un momento.
Versus a cold.
I'm slow, okay?
Wait. Oh, sorry. It's okay.
Is that clock right?
Yeah, I got
Is it right? Oh, okay, because I know that one's wrong. That one's
Computer
wrong.
ones, yeah. That one's right. That one.
Okay.
Yeah, I thought
I say that's why I'm late to like every meeting. Okay, the squaring function. I think the productive lapse in time is now over. So, quadratic.
But didn't we already do squaring?
Yeah, we didn't fill in the characteristics yet. Silly goose. We're going back and we're filling in.
Yeah.
Quadratic. So the standard form is y equals ax squared plus bx plus c. Although there is a much nicer form, which is y equals a times x minus h squared plus k. That we'll see when we go a little bit more forward in chapter 1. I know. They might just be walking. Maybe we shouldn't say they're stopping.
Maybe like the base of the computer will have like more. You need a really strong base, then you'll have.
Anyway, so we have our squaring function. Any squaring function, well, hold on. We know what shape it is, right? Isn't it the shape of a parabola? we have when a is greater than 0, which is not the slope, Parabolas have slopes, but it's a bit more complicated than m. Actually, it's a lot more complicated. Actually, it's kind of where calculus comes from. Anyway, I wanted to point out the vertex. There's a vertex to every parabola. If you have it in the snazzy form, it's actually pretty cool because the vertex is at HK.
Whoa.
But the problem is you have to complete the square sometimes to get there. Which is why that's in chapter 2 and not in chapter 1. You're welcome, I think. I might actually end up eating my words, but I think it's in chapter 2. Okay, so vertices can either be maximums or minimums. So we could say that the vertex in this one would be a min. Can anyone tell me why? Versus the vertex being a max in this one. That's how it opens up. Good. Because if a is greater than 0, it's concave up with a cup. So my vertex is at the bottom of that concavity. That's up. My parabola is upwards facing. And if a is less than 0, it's concave down like a frown. And you can think of negative people frown more, positive people smile more. Well, that's always true, but kind of.
Happiness is on the inside.
Well, what's on the inside comes out. Think of the happiness that comes out.
That's what the inside comes out.
Out of the heart, the mouth speaks. So if you're happy on the inside, you shouldn't necessarily always be wearing a scowl.
What book of the Bible was that from?
Proverbs?
It's in a lot of verses.
I mean, the idea is in it.
I don't know.
In Proverbs, it talks about how, what's the bitter water and the sweet? Take a picture.
I said water into wine.
What direction are you headed? Anyway, so we have our parabolas, we have our quadratics, we have our opening up and our opening down, and our vertices that can be maximums or minimums, and I've given you a hint that this guy has slopes, plural, has slopes, but how to find them are way more complicated and actually kind of lead to calculus. Cubic. Cubic. So cubic functions are not quite as exciting. This is the parent function. The parent function is a super basic y equals x cubed. We could go ahead and I'm going to do it for this. Well, I'm not exactly sure what I want to say. Because x squared has like a super nice ax squared plus bx plus c. Like it can be transformed with all these like shifts and dilations and translations, all this stuff. This one can be too. The only problem is I don't want to make a big deal about it because we'll deal with it when we get to transformations in section 1.7 or 8 or 9. So, video. Jaden, if you want to find it. If you don't want to watch the video, there's the PDF.
So no homework?
So homework due Monday? If I don't change it, you're going to call me on it.
So Tuesday. Well, I'm
Jaden,
still
if you don't win, we're
thinking,
gonna coach.
I'm still thinking Tuesday, so.
No, you're not.
No, just keep it.
Because I'm shouting Monday as you walk.
Yeah, I gotta watch NFL on Sunday.
Which means you need to have it done before Sunday.
Why is it in one day?
And I'm gonna be tired.
Because I remembered wrong. I looked at the calendar like we should all do, and I realized.
Jaden, if you
So
don't
on
win,
Tuesday.
we're gonna coach.
So Monday.
Tuesday.
Have fun at the game. Monday.
Tuesday.
Bye.
Okay. We could go ahead and throw a quick. No, it's not. Let's do this. For x greater than 0, what I want you to see, one of the biggest things about a cubic versus the other ones, it's going to be noisy. There's football players that are in the hallway. Just hang in there. Is that if x is positive, a cubic function is positive. Like the y values are positive, and if x is negative, the cubic function is negative. Remember with squared, the signs will stay the same, but with cubes, the signs will change, they'll flip. And because of that, we don't have a max, we don't have a min, but what we do have, the testings up on you, wow, is a point of inflection. So we don't have a vertex, that's not a thing, it doesn't have a max or a min, but we do have a point of inflection. Here's something interesting we haven't been talking about yet. Question, linear, quadratic, cubic, and quadratic is squaring. Have any of them had limited domains or ranges?
Yes.
Which one? Or ones?
Squaring.
The squaring function, how is he limited?
Minimum and maximum.
Minimum or maximum, so there is a highest or there is a lowest? Yes, I agree. So really quickly, if we were to come back here to the parent function, the super basic guy with no transformations whatsoever, what would his domain have been? What are the questions we're supposed to be answering? Remember the little windows that open? How far? Left to how far? And what's true about these little quadratic dudes? Just keep going. So all real numbers for domain. So that wasn't limited. Ha! You're wrong unless you're right. What's the range?
Y is greater than or equal
You could do interval notation, which would be 0 to infinity, or you could do just greater than or equal to 0. Are we good? But what about the cubic or the linear? Are either of them limited? Is the linear or the cubic, are either of them limited? Yeah, good. So the cubic will keep going, so how left, how right will he go?
Axis of symmetry.
Cool. What's his domain? Why is it all real numbers? Because it's forever left, forever right, yeah? What's its range?
All real numbers.
All real numbers. What about lines? Ah, all real numbers, all real numbers. Wait. Ooh, except, what are the two that are going to have limited domains or ranges?
Constant.
Because a constant is only, this one, is only 1y and forever left, forever right. So all real numbers domain, or 1x, forever up, forever down, right? So only the weird lines, only the horizontal. Maybe I shouldn't use the word weird. Might make him feel bad. Anyway. Okay. Only the horizontal vertical ones. Weird isn't a bad thing, right? We're all weird in our own weird ways. Anything else about cubic? Oh, there is. There is one thing. A point of inflection. I just want to describe it really quickly. Do you guys know what the word inflection means, even outside of math?
It's like to inflect something.
It's like when something is like. It's like when you put like a straw in a cup of water. It's like not the other way around, but like it's kind of. No, but it's like this. It's like when you look at it, it goes like that kind of.
Oh, that's not what you're thinking.
It's when you
That's,
inflect.
oh, what is that? Wow, it just flew out of my head. Who has it?
Can I
When the straw looks a little bit like broken.
That was me. When you put it in the water, it looks
I
kind
know,
of
but it's
tilted.
not this.
I need to look it up. Diffraction.
Is that it?
Or can see something smart like
I was thinking it was refraction.
Cass's IQ is too
It's not
high.
reflection, because that's like a mirror, although it flips. I think it's refraction.
I should look it up.
But anyway, inflection. No, I got this. Anybody else have inflection though? I mean, I know this one.
Is it inflection like when something inflects? When it like
Someone Google it.
Mathematically, we can call a point of inflection a point at which concavity changes.
What's concavity? The way it can.
That's a great question, and I'm glad you asked it. Concavity is smile to frown or frown to smile.
What?
Do you see this one changing from frown to smile?
No.
Depressing. Oh yeah.
See?
It's
It's a half frown and it's a half smile.
It's a smirk.
Oh, sure.
It's a smirk.
But not. So this is technically a concave down, but it's missing the other side. Yeah, but this portion is still, or it has, or it maintains a concavity that is down, and then a concavity that is up. Another way of saying it is that it's rising slower and rising faster, if we want to go like super snazzy and calculus-y. But concavity has to do with the whole smile frown dealio, and it doesn't have to be a full concave down to be concave down. Or a full concave up to be concave up. It can be a part of it.
Like what it flips diagonally?
Yeah, like kind of like the origin symmetry, like that flipping. We didn't say that. But in like life, if someone has good inflection, like if they're in theater or something, or if they're doing like a reader's theater, or they're reading out loud. Ooh, reading out loud, English class. You do like a choral reading, or not choral, popcorn reading sometimes, right? Like you read, then you read, then you read. What's an exciting reader versus a boring reader?
Exciting.
Someone like David Hobson.
Whether or not they have inflection. If someone just reading a story like this because they're just trying to read, and they're just like, I'm just reading, I have no idea what's going on, I'm just saying the words, I'm trying to say the words really carefully, and it's just like this, it's like the, right? They have no inflection. Their intonation does not change. But if you have inflection, then you're going to be expressive, and you're going to see a guy who says, oh no! And you're going to say, oh no! And you're going to go, oh, I'm sad. You're going to say, I'm sad. And you're going to go through the story in a way that you're actually trying to relate the story to someone who's listening. And you're actually thinking about what's being said and how it should be said and how to get the feelings across. Anyway, inflection. You can think about sound waves and all that kind of stuff, but we're not talking about waves. We're not talking about sine and cosine today, so we have to keep going. Alright, who is next? Square roots. Square roots are weird because they have restricted domains and ranges. They're the first one thus far. Restricted domains and ranges. So the parent function, how far left does the square root go? 0. No, you're right. 0. Does it hit 0 or does it not? Woo! Remember domain problems with even-powered roots? They're always, the argument always needs to be greater than or equal to 0. So the graph shows it hits 0 and stops. But also our domain understanding of, negatives don't belong under there might help you also. But the weird thing is that the range is also restricted. Now, just because these two match doesn't mean they always do once we start translating and stretching and dilating and flipping and all that stuff. The square root functions go and then they stop because of that whole negative thing. Can we not? Party poop. Now, the dealio with square root functions, though, if you're thinking about representative points, up until this point, it's been like you could plug in -2, -1, 0, 1, 2 to a table and get like pretty indicative points as far as like, oh, hey, it's squaring. Oh, hey, it's cubing. Oh, hey, it's linear. This one's a little bit weirder because if you were to set up a table to try to graph a square root function, you need to be careful because not all square roots are nice numbers, right? So if I was setting up a table for this, I would go from 0 to 1 to 4 to 9. Does this all make sense?
Wait, what?
Because square root of 0 is 0. That's easy.
Oh, really?
Square root of 1 is easy. Square root of 4 is easy. Square root of 3 and square root of 2. Be Mrs. Leon and know the decimal equivalents off the top of your head. But otherwise, just skip the ugly ones. Skip the messy ones. Don't
That's
make
not
it.
very nice.
I know. That's why I had to reword it. Although it's okay, because I admit that I have ugliness and I have messiness. I'm not judging necessarily their ugliness or their messiness. Besides the fact it makes them a little bit more difficult. There's a life lesson in there somewhere. But anyway, let's keep going. Sometimes I personify math. It makes it more fun. Like I have friends. Just kidding. So, just wanted to show you a quick little, like, hey, for a table, he would not be a very smart one just to go by ones or something, because you would want to go by the nice perfect squares, yeah? Besides that, it only has one concavity. I guess we could talk about that. Is there anything else that you guys notice about the graph? He keeps going forever, but only in one direction.
I like 8 t-shirts without
We could say even, yeah, if we were doing like the interval notation, yeah, it would be like 0 to infinity. Remember? The half open and 0 to infinity. All even powered roots are similar. Now in calculus, if you guys look up there at theirs, in the sense of similar shape, and they all come down to a point, and they can't keep going after that. Calculus doesn't stop at the square root. We go farther, and we talk about a cubed root, because cubed roots or fifth roots or seventh roots are different. You're allowed to have negatives, so it's going to keep going. It's going to look like the cubic, but inverted. Ooh, inverse functions. That's like a couple chapters later. Anyway, good stuff, but let's keep going. Reciprocal function. 1 over x. You guys probably couldn't read that light blue writing. 1 over x. Calculus goes farther and also talks about 1 over x squared. That we have an even or we have an odd. What do you guys notice about his graph? Yeah, it has origin symmetry. We could talk about that. It does have origin symmetry. Actually, no, but that's an interesting observation. Do you guys see it goes from down to up? But what's the in between the concave down and the concave up? Not a point. What's this guy? Vertical asymptote.
Asymptote.
Helps you remember how to spell it. Asymptote. So it does have a vertical asymptote. because it has a vertical asymptote, I also have a domain problem. Wait, we should know that already, right? Because what is the denominator? In this case, super, super basic, just x. What is he not allowed to be?
0, negative x.
He is himself, but he's not allowed to be 0. If I divide by 0,
the
that's some
asymptote.
issues, right? Huh?
Because of the asymptote.
Yep. Or is it the asymptote because of him?
The no touchy.
Thou shalt not pass. Vertical asymptote at, in this case, x equals 0, where the 0 is at the denominator. That gets sticky. I won't write that. Because you can have zeros in a denominator that aren't vertical asymptotes. So. But there is a vertical asymptote at x equals 0, which means the domain x can't equal 0. But we also have, do you guys see the other guy? Who's an
horizontal asymptote.
I do, because he's getting closer and closer and closer. Now, ironically, horizontal asymptotes, graphs are allowed to pass, but this one doesn't.
Because of
Graphs are allowed to pass horizontal asymptotes. That's kind of weird. Most people think that's not a thing. So it's allowed to pass. Vertical asymptotes never. Those are domain problems. Horizontal asymptotes, ironically enough, they are allowed to pass, but this one doesn't. So we can put him down also. And yeah, you guys are right. He does have a concavity change, but not at a point, so I can't call it a point of inflection. So, can't do that. This is something to notice that, just like with the x cubed, this guy can be positive, he can be negative, he can be above, he can be below because of the odd power of the x. Not a big deal. We got it? Okay. What about pieces? So I gave you an example of a piecewise, kind of a hard one, because he has 3 pieces. You see them? Piece 1 and piece 2 and piece 3. And depending on how the pieces are set up, you might have x like less than or equal to an a, and then you might have x like greater than that a, but less than or equal to, or just less than a b, and then maybe x has to be greater than or equal to a b. And that's if they're including all real numbers, so going less than to negative infinity, going greater than to positive infinity. Sometimes a piecewise only is contained. So I can't really talk about domains. I can't really talk about ranges, because who knows who's going to show up in this piecewise function and what his behavior is going to be. And who knows if these pieces even connect or if they disconnect. So piecewise functions are super complicated only in the sense that I don't know what's going to show up. And so until I know who's there, I can't really tell you domains or ranges or concavities or anything. Because what if they're just 3 pieces of line? Well, it's going to be great, but lines don't even have concavity. They don't inflect at all. They just go at constant slope. But these 2 guys down here, even though I can't tell you much, before we get to these 2 special piecewise functions, what I can tell you is when you have a graph, these little intervals split up the x-axis in different portions. So let's just pretend that A is here. Let's just pretend that B is here. I don't know. I'm making it up. They could be shifted over or shifted back. But piece 1 would need to go in this region, right? F of x would be graphed here. True? Whoever he is. He'd be graphed to the left of A and up to and including A, right? So up to and including A because it's closed at A. H of x would be, oh sorry, not F of x, G, I apologize. Who is F, but H would be here, and J would be here. Anybody know why I didn't put I?
Because there's no int.
Maybe. No, because I in math is actually the square root of -1. It's an imaginary number. So that might get confusing. We have G, we have H, we have J. I have a little bit of time. Let's see. A comparison of a piecewise function. I have a good real life example for a step function. Absolute value, I don't think we really need one because you guys are so used to it. But a piecewise function. What's some sort of business that works in teams? Like the employees work in teams, where they have different roles. Huh?
Every business?
Yeah, but give me an example of one.
Amazon.
Like a guitar factory.
Yeah,
Like some people make a neck,
Something
and
like-
some people make the body, some people make the
Yeah, you
pickups.
could do that. I suppose. Firefighters? I'm not versed enough. Yeah, you're right. You guys are all right. I need to find one that I'm actually knowledgeable of. Let's use Starbucks. Just because they're super particular about the roles that their employees do. You go ask Mr. Is it Graff or Grop? Have you guys heard? It's Graff, right? I heard Grop and I was like, are you sure?
Mr. Green. Wait, he's still.
Anyway, Mr. Graff, he's a barista. I'm not sure if he's still currently one, but
Yeah.
yeah.
Wait, he worked at
He works in CD, I think.
At the one. My brother said he used to work at
He looks like a hardcore barista.
He doesn't work on the Cochrane one, does he?
He does.
With the
his
hat,
hat.
Target
hat,
and
dude.
Trader Joe's?
He looks like a hardcore.
He does look like a.
He does.
Yeah, he does.
Hardcore.
And his personality's kind of like it too.
Yeah, exactly. Yeah.
So anyway, it makes it perfect for a teacher. Come back, Starbucks. In little coffee chains, if you have multiple people working, like little privately owned ones, they're like, okay, who cares? Like if you're here at the cash register and if something's going on over there and there's no one at the cash register, just go help. Like you can just go fill whatever role you want. You can wear all the hats. At Starbucks though, they're like, no. If you're on shift here, you can't go over there. You need to stay here, you need to stay available, you need to stay exactly in your position. So that's kind of what I was referring to. So if piecewise function, there is a crew that's on shift at Starbucks, right?
Yes.
Between this time, between that time, there's a crew. They're the overnight crew or whatever, or they're the early morning crew. Super early morning.
Overnight crew, bro.
So they're depending. Some Starbucks are open pretty late, and some holidays are open even later.
Yeah.
Never mind. Coming back. Coffee Bean did like these all-nighter things during the CSUN's like finals week last semester, and yeah, and they like offered discounts or free shots of espresso or something ridiculous. Anyway, coming back. I don't know if Starbucks is open overnight usually, but we have the early morning shift. Stop. Early morning shift. But do we have people in different roles that have different jobs?
Yes.
Yes. And they're not supposed to, at least at Starbucks, they're not supposed to interchange. You're supposed to stay here, be at the hot bar, stay here, be at the Frappuccino bar, stay here at the window drive-thru, well, they all kind of do the drive-thru. But, coming back, they have their job. So it's one of those where this is saying, hey, is it legal or not? Hey, are you supposed to be at the cash register? Then you're supposed to be doing this. Hey, are you supposed to be at the hot bar? Okay, you're supposed to be making the hot drinks with the espresso machine, etc. Hey, are you, see what I mean? Each job has certain job descriptions, but you need to be in that certain role for you to be doing those tasks. That's kind of like a piecewise function. So if you're trying to graph x less than or equal to a, you need to figure out, okay, wait a minute, well, where is this true? Oh, x less than or equal to a is here. That's where I put g. Or x is in between a and b here. That's where I put h, etc., etc., etc. Now, these two are special piecewise functions. So, special, ooh, that's awkward. Special piecewise. So they're not separate. If you guys notice, they're actually underneath the piecewise umbrella. True? Okay, so why are they special and who are they and what do they do? If I was to show you these guys in their piecewise definitions, the absolute value is probably the most confusing one because you guys have seen him since, I don't know, middle school, right? Yeah. Absolute value. Everybody remembers him in that you put in a negative, what comes out?
A positive.
And put in a positive, what comes out?
A positive.
Wait a minute. So, depending on what goes in, this function does different things to pop things out, right?
For us.
So, depending on the input, do you guys remember that inputs are x's?
Yeah.
Depending on the input and whether it is a positive input or whether it's a negative input, different things occur. If you put a positive input into absolute value, just leave it as a machine, what does it pop out?
Positive.
So what happens to x if he goes in a positive 2, what's coming out?
Positive 2.
The exact same thing. If you put in an x, you get out that exact same x. For positive numbers, you put them in, they come out the exact same. Nothing changes. But for negative numbers, so if x was negative 1, what comes out? If x is negative 5, what comes out? If x is negative 17 halves, what comes out?
So 17.
The sign flips. And mathematically, how do we flip a sign? Multiply by a negative. It looks weird, and yet it is so stinking true. Sometimes absolute value keeps it the same, and sometimes absolute value makes it the opposite. A lot of people look at this and they say, no, he can never be negative. Negative numbers times a negative make a positive. Yes, he can.
Wait, so in theory, wouldn't it you only be able to have positive values on it, on the graph?
Exactly. Which is exactly what we see. Only positive function y values.
Oh.
But negatives or positives can go in. Negatives or positives of x's can go in. But the function values are always positive. Not much of a struggle, huh? Hang on.
It's cool.
So the function values are positive. So absolute value is actually a piecewise, and this is a super important thing for pre-calc and calculus and the other calculus and all sorts of things. This guy's a bit more complicated, and the best illustration that I can give to you for him, you guys see the double brackets now? It's a parking garage. The best one I can give you for him is a parking garage.
Why is it?
Because if you get your first hour free, they're like, hey, if you're in the parking garage from 0 to 59 minutes, it's free. But as soon as you hit that hour mark, guess what? They're like, now we can charge you. Literally, I did this the other day down at, where was I? Down at here somewhere. And I was like right on the 2 hour mark. The first 2 hours were free, and I was like, you charged me! Because they say go 1 second over, and all of a sudden, nope, now you're up here. Oh, nope, now you're up here. See how it goes in homework due on Monday. The hardest thing is going to be the step function. Check out exam. Keanu. Hello. Testing.
Oh, Misty. My chocolate heard testing.
That's what happened. If I was the chocolate, I might have done it too. Oh.